You have probably seen the claim already. It shows up in 1,000 different videos with 1,000 different thumbnails, all promising the same impossible idea. Distance does not exist. Space is a lie. The gap between you and the farthest galaxy in the visible universe is, in some deep sense, zero. And usually, somewhere in the description, there is a name attached to make it feel credible. Einstein said this. Feynman proved that. A quantum experiment confirmed it. The claim spreads because it feels like forbidden knowledge, the kind of thing that should be in a physics textbook but somehow isn't, hidden from you by a curriculum that never wanted you to look too closely at the walls of the universe. So we are going to look closely. We are going to take this claim into evidence, and we are going to find out exactly how much of it survives contact with the actual physics and how much of it is built on a half-truth stretched past its breaking point. Here is the honest version of the claim, the part that is genuinely true and genuinely strange enough that nobody needed to exaggerate it. If you could somehow ride along with a photon of light from the moment it leaves a star to the moment it strikes a telescope mirror on Earth, your onboard clock would not advance at all. 0 seconds. Not a very small number. 0. This is not a rounding error, and it is not a metaphor. It follows directly from the mathematics of special relativity, the theory Albert Einstein published in 1905 in a paper titled On the Electrodynamics of Moving Bodies. In that paper, Einstein worked out what happens to time and space when something moves at a constant velocity relative to something else. And one of the strange consequences is that as an object's speed approaches the speed of light, the amount of time that passes for that object, measured on its own clock, shrinks towards 0. Push the math all the way to the speed of light itself, and the elapsed time hits exactly 0. Photons, as far as we can tell, always travel at exactly that speed in a vacuum. So if you did the impossible thing and asked a photon how long its journey felt, the honest answer, according to the equations, is that it felt instantaneous. No duration, no experience of time passing at all. This idea has a proper name in physics. It's called proper time, and the quantity that goes to 0 for light is specifically the proper time along a photon's path through spacetime. We covered this in detail in an earlier investigation on this channel, walking through exactly how the mathematics forces this conclusion and what physicists mean when they say a photon experiences no time. If you haven't seen that one, it sets up everything we're about to build on here, because this video is not a repeat of that case file, it's the next one. Because once you accept that light experiences 0 time on its journey, a second, much more loaded question opens up right behind it. And this is the one that all those viral thumbnails are actually trying to cash in on without ever properly investigating it. If distance and time are tied together the way relativity says they are, and if time collapses to nothing for something moving at light speed, does the distance collapse too? And if it does for light, does it also collapse for you? Is the yawning gap between Earth and Proxima Centauri, 4.24 light-years of empty space, actually 0, sitting right there disguised as an enormous distance? That is the actual investigation today, and the answer is going to surprise you less because it is fake, and more because the real version is stranger and more carefully constrained than the fake one. And once you see how it's constrained, you'll understand why so many videos skip that part entirely. To get there properly, we have to rewind to 1908, 3 years after Einstein's original paper, when a mathematician named Hermann Minkowski stood up and gave a lecture that reframed the entire theory. Minkowski had been one of Einstein's professors, and by his own account, he was initially skeptical of the young patent clerk's ideas. But working through the mathematics, he realized that special relativity made far more sense if you stopped treating space and time as two separate things, and started treating them as a single four-dimensional structure, which he called spacetime. In a now famous line from that 1908 address, Minkowski declared that space by itself and time by itself were doomed to fade into mere shadows, and only a union of the two would preserve an independent reality. This wasn't poetry for its own sake, it was a precise mathematical claim. In Minkowski's framework, what stays the same for every observer, no matter how fast they are moving relative to each other, is not the distance between two events, and not the time between two events measured separately. It's a combined quantity called the space-time interval, which mixes space and time together in a specific mathematical way, with a crucial minus sign that makes it behave differently from ordinary distance in three-dimensional space. That minus sign is the whole story, so it's worth sitting with it for a moment. In everyday three-dimensional space, if you want the distance between 2 points, you square the differences in each direction and add them together. Spacetime works almost the same way, except the time part gets subtracted rather than added. This has a strange consequence. For something traveling at the speed of light, the spatial part and the time part of that calculation cancel out exactly. The spacetime interval along a light ray is precisely 0. Physicists call this a null interval or a light-like interval, and it's not an approximation or a special case that only shows up under unusual conditions. It's baked into the geometry of relativity itself. Every photon everywhere at every point in its journey traces out a null interval. So when someone says the interval distance a photon travels is 0, in this very specific four-dimensional sense, they are stating something Minkowski's geometry actually says. This is the seed of truth. This is the honest kernel that the viral claim starts from. But here is where the reframing has to happen, because this is exactly the point where the popular version of the story quietly swaps one thing for another and hopes you don't notice. The null spacetime interval belongs to the photon's own trajectory. It does not belong to you, standing on Earth, looking up at Proxima Centauri. When we say the star is 4.24 light-years away, we are not talking about a spacetime interval measured along a beam of light. We're talking about a spatial distance measured within a single reference frame at a single moment in what that frame calls now. Earth's frame, roughly speaking, since Earth is moving so slowly compared to light that we can treat it as very close to being at rest for it. In that frame, distance is a perfectly ordinary, well-defined, non-zero quantity, calculated the way distances have always been calculated. And it does not shrink to 0 just because somewhere else in the universe there exists an object, a photon, that experiences its own path differently. You are not the photon. You do not get to borrow its 0. That's the mistake. That's the entire trick the thumbnails are running. Before we get to relativity of simultaneity itself, it helps to picture the thought experiment Einstein actually used to introduce it, because the abstract version of this idea can slide past you if you're not holding a concrete image. Imagine a long train moving at a steady speed, and imagine lightning strikes both ends of the train at once, leaving scorch marks on the track. A person standing on the embankment, exactly halfway between the two marks, sees both flashes of light arrive at the same instant and concludes the strikes were simultaneous. But a passenger sitting in the exact middle of the moving train sees something different. Because the train is moving forward, the passenger is rushing toward the light coming from the front strike and moving away from the light coming from the back strike. The light from the front arrives first. From the passenger's point of view, the front lightning struck before the back lightning did. Neither observer made a measurement error. Neither one is wrong. They simply belong to different reference frames, and at the same time turns out not to be a fact about the universe that everyone agrees on. It's a fact that depends on how you're moving. This single thought experiment, worked through carefully, is the seed from which the rest of special relativity strangeness grows, including the frame dependence of distance itself. Let's make this concrete with an idea called relativity of simultaneity, which Einstein worked out in that same 1905 paper. Two events that look simultaneous to one observer might not look simultaneous to another observer moving at a different velocity. This is well established and experimentally confirmed, and it means that different observers really can disagree about the order and separation of events depending on how fast they are moving relative to each other and relative to the events themselves. This is genuinely mind-bending. It means distance and duration are not fixed, universal quantities handed down from on high. They depend on your reference frame. A muon created in the upper atmosphere by cosmic rays, for instance, has an extremely short lifetime in its own resting frame. So short that under naive assumptions it should decay long before reaching the ground. And yet we detect huge numbers of these muons at sea level, a fact confirmed repeatedly since the famous Frisch-Smith experiment atop Mount Washington in 1963. From Earth's frame, the explanation is time dilation. The moving muon's internal clock runs slow relative to ours, so it survives long enough to reach the ground. From the muon's own frame, the explanation is length contraction. The distance through the atmosphere is shorter than we measure it to be, so it doesn't need as much time to cross it. Both explanations are correct in their respective frames, and both have been tested and confirmed. Distance really is frame dependent. This part of the claim is completely real. So does that mean any observer, including you, could in principle experience the distance to Proxima Centauri as 0? Here's where it gets interesting rather than fake. If you build a spacecraft capable of accelerating close enough to the speed of light, and if you could somehow survive the acceleration, then yes, in your onboard reference frame, the length contracted distance to Proxima Centauri would shrink dramatically. Push your speed close enough to light speed, and that contracted distance approaches zero, matching what an actual photon experiences. This is real physics, and it's been confirmed indirectly through decades of particle accelerator experiments, where particles accelerated to a large fraction of light speed behave exactly as length contraction predicts. It's also the same underlying mechanism behind the famous twin paradox, where one twin stays on Earth and the other travels on a high-speed round trip to a distant star and back. When the traveling twin returns, they are measurably younger than the twin who stayed behind, a consequence that has been directly tested using precision atomic clocks flown on aircraft. First in the Haefel-Keating experiment in 1971, where two physicists flew cesium atomic clocks around the world on commercial airliners and found the tiny but exactly predicted time differences relativity calls for, compared to a reference clock that stayed on the ground. The traveling twins' shorter elapsed time and the traveling twins' contracted view of the distance they crossed are two descriptions of the same underlying fact, seen from two different angles of the same reference frame. So the honest, fully qualified version of the claim is this: distance is not a fixed, frame-independent fact about the universe. It depends on how fast you are moving relative to what you're measuring, and for something moving at exactly the speed of light, that distance mathematically goes to zero. But for you, standing on Earth, moving at ordinary human speeds, the distance to Proxima Centauri is not zero. It is 4.24 light-years, full stop, in your own reference frame. And no fact about photons anywhere else in the universe changes that number for you. This is the point in the investigation where we bring in the reality check, because there is a second layer to this myth that goes even further off the rails than the relativity confusion, and it deserves its own scrutiny. A large share of these viral videos don't stop at special relativity. They reach for quantum entanglement, the phenomenon where two particles can be correlated in such a way that measuring one instantly tells you something about the other, no matter how far apart they are. This was tested rigorously through what are called Bell tests, based on a theorem published by physicist John Stuart Bell in 1964, and experimentally confirmed with increasing precision starting with John Clauser's experiments in the 1970s, then Alain Aspect's landmark experiments in the 1980s, and finally the loophole-free Bell tests conducted around 2015 by groups at Delft, NIST, and in Vienna. In 2022, Clauser, Aspect, and Anton Zeilinger were jointly awarded the Nobel Prize in Physics specifically for this body of work on entangled photons and Bell inequality violations. This is genuinely one of the most well-tested results in all of modern science, and the temptation to over-interpret it is enormous, because entanglement really does look from a certain angle like distance stopped mattering. Here is the reality check, stated as carefully as the physics demands it. Entanglement correlations are real, experimentally confirmed, and genuinely strange. But they do not allow any usable information, signal, or influence to travel faster than light, and they do not eliminate or erase the physical distance between the two particles. This is formalized in what's called the no communication theorem, a mathematical result showing that no matter how cleverly you try to exploit entanglement, you cannot use it to send a message faster than light. If you measure one particle in an entangled pair, you learn something about its partner instantly, but you cannot control what you measure, and your partner sitting light years away cannot detect anything different about their particle until information about your measurement reaches them by conventional means, at or below the speed of light. Einstein himself famously called this behavior spooky action at a distance in a 1935 paper co-written with Boris Podolsky and Nathan Rosen. And the entire history of Bell test research since then has been about pinning down exactly what that spookiness does and does not permit. What it does not permit is the erasure of distance. The particles remain exactly as far apart as they were. The moment the correlation is measured happens exactly when relativity says it should happen from each observer's frame, and nothing about entanglement means space itself has folded up or vanished. When a video tells you quantum entanglement proves distance in space is fake, it is taking one of the most carefully verified results in physics and attaching a conclusion to it that the physics explicitly forbids. That's not a nuance. That's a direct contradiction of the no communication theorem, one of the most solid results built on top of entanglement research. This is also a good moment to correct a second, related myth that tends to ride along with the entanglement confusion. The idea that relativity somehow implies wormholes or shortcuts that let you skip distance altogether, the way science fiction loves to portray it. Wormholes are, in fact, mathematically permitted solutions to Einstein's equations of general relativity, first explored in a 1935 paper by Einstein and Nathan Rosen. But every known solution requires forms of matter and energy that have never been observed to exist in the amounts or configurations needed, and nothing about their mathematical possibility means space has secretly always been foldable for ordinary objects like us. Distance remains the governing structure of the universe we actually inhabit. The theoretical loopholes physicists study are precisely that, loopholes worth studying rigorously, not evidence that the rule they'd have to violate isn't real in the first place. Every legitimate physicist working on these ideas will tell you the same thing. The interesting part of the story is how tightly constrained the loophole is, not how easily it lets you escape the rule. There's a deeper structure underneath all of this worth naming directly, because it explains why light behaves so differently from everything else. The light cone. At any single point in spacetime, the set of all paths light could take, forward and backward, forms a cone-shaped boundary that divides the universe into what can causally affect that point and what cannot. Nothing with mass can catch up to or exceed the edge of that cone, which is exactly why light speed functions as a cosmic speed limit rather than an arbitrary one. Distance, in this picture, isn't just a number on a ruler. It's a statement about causal structure, about what can possibly influence what. And it's precisely because light rides the very edge of that structure that its own proper time and spacetime interval collapse to zero, while everything with mass, including you, is confined to a slower path through spacetime, where distance behaves the way our instruments and our intuition mostly expect. So where does that leave the actual claim, once you separate what survives from what doesn't? Distance is real, in the sense that matters for you, for me, for every observer moving at ordinary speeds relative to the things we're measuring. It is a well-defined, measurable, physically consequential quantity, and we have spent more than a century building increasingly precise tools to measure it across the universe. The cosmic distance ladder, as astronomers call it, starts with something as simple as parallax, the apparent shift in a nearby star's position as Earth orbits the Sun. First used to measure stellar distances successfully by Friedrich Bessel in 1838 for the star 61 Cygni. It extends outward through standard candles, objects like Cepheid variable stars and Type 1a supernovae, whose intrinsic brightness we can calculate, letting us compare how bright they appear to how bright they actually are, and back out a distance. It was precisely this kind of standard candle measurement, applied to distant supernovae, that led Saul Perlmutter, Brian Schmidt, and Adam Rees to their 1998 discovery that the universe's expansion is accelerating, work that earned them the 2011 Nobel Prize in Physics. Beyond the reach of standard candles, astronomers rely on redshift, the stretching of light's wavelength as space itself expands between a distant galaxy and us, a relationship first laid out systematically by Edwin Hubble in 1929, when he showed that galaxies farther away recede faster, in direct proportion to their distance. That proportionality, now called the Hubble-Lemaitre relation, in recognition of Georges Lemaitre's earlier theoretical work, only makes sense as a distance measurement if distance itself is a coherent, real quantity that redshift is a reliable stand-in for. Every rung of this ladder, from parallax to standard candles to redshift, has been cross-checked against the rungs above and below it for decades, and the fact that they consistently agree is itself strong evidence that distance is not a fiction physicists quietly gave up believing in behind closed doors. None of that research would mean anything if distance were an illusion. The entire edifice of modern cosmology, every measurement of how far away every galaxy sits, every calculation of how the universe has expanded over nearly 14 billion years, depends on distance being a real, measurable, physically meaningful quantity, even though, and this is the crucial twist, that quantity is frame-dependent rather than absolute in the way Isaac Newton once assumed it was. That's the actual reframing this case file has been building toward. The pre-Einstein picture of the universe treated space as an unchanging stage and time as a universal clock ticking the same for everyone, everywhere. Einstein and Minkowski replaced that picture with something more flexible and, honestly, more elegant. A single four-dimensional space-time where space and time trade off against each other depending on how you're moving, but where certain deeper quantities, like the space-time interval, remain fixed and universal no matter who's measuring them. Light lives at the extreme edge of that geometry, tracing out intervals of exactly zero, which is why a photon's proper time is zero, and why, if you pushed a massive object close enough to light speed, its measured distances would shrink dramatically too. But you and I are not living at that edge. We are moving at ordinary speeds, and in our own reference frame, distance behaves exactly the way our instruments, our telescopes, and more than a century of astronomical measurements say it does. It is real. It's just not the fixed, frame-independent backdrop that intuition wants it to be. There's a human cost buried in this story that rarely gets mentioned, and it's worth sitting with before we close the file. For most of scientific history, distance was treated as one of the most solid, unquestionable facts about reality, something you could always fall back on, no matter how strange the rest of physics got. Einstein's insight took that certainty away, and it did so at a real personal cost to how physicists had to reorganize their entire way of thinking about the world. Minkowski himself died in January 1909, just months after delivering the lecture that gave spacetime its modern mathematical form, and never lived to see how completely his framework would come to define 20th century physics. The generation of scientists who came after him had to rebuild their intuitions from scratch, and in some ways we're still doing that rebuilding today, every time a new experiment forces us to reconcile our gut sense of here and there with the stranger truth the mathematics keeps confirming. That discomfort is not a flaw in the science, it's the whole reason this subject keeps drawing people in. And it's exactly the discomfort that clickbait videos exploit by offering a simpler, falser answer instead of asking you to sit with the real complexity. Minkowski's four-dimensional spacetime also opened the door to a philosophical picture some physicists call the block universe, or eternalism. The idea that past, present, and future all exist equally within the four-dimensional structure of space-time, rather than the present moment being the only thing that's real, while the future waits to be created. Einstein himself gestured toward this view late in life. In a 1955 letter written shortly before his death, consoling the family of his close friend Michele Besso, he wrote that people like them, who believed in physics, know that the distinction between past, present, and future is a stubbornly persistent illusion. That line gets quoted often, sometimes twisted into supporting the same "everything is an illusion" framing this investigation has been picking apart. But Einstein wasn't saying space and time don't exist. He was pointing at something much more precise, that the flow of time, the felt sense of now moving forward, isn't a built-in feature of the equations the way distance and duration are. It's a subtlety, not a demolition, and subtleties don't survive being flattened into a thumbnail. And the practical stakes of getting this right are not abstract. Relativistic corrections to distance and time aren't confined to thought experiments about photons and spacecraft near light speed. Every GPS satellite orbiting Earth carries onboard atomic clocks that run measurably faster than clocks on the ground, a combined effect of special relativity, because the satellites are moving relative to us, and general relativity, because they sit in a weaker gravitational field farther from Earth's mass. If engineers didn't correct for these effects, GPS positioning would drift by roughly 10 kilometers a day, rendering the system useless within hours. That correction is applied constantly, silently, every time your phone tells you where you are. Specifically, special relativity predicts the satellite clocks should run slightly slower due to their orbital speed, while general relativity predicts they should run faster due to sitting higher up in Earth's gravitational field, farther from the mass that curves spacetime and slows clocks near it. The two effects don't cancel out. The general relativistic effect wins out, and the net result is that GPS satellite clocks are deliberately built to tick at a slightly different rate before launch, precisely offset so that once they're in orbit and experiencing both relativistic effects simultaneously, they end up synchronized with clocks on the ground. Engineers at the United States Naval Observatory and similar institutions manage this correction as a routine, unglamorous part of keeping the system accurate, and it has been running continuously since the first operational GPS satellites launched in the late 1970s and early 1980s. The same relativistic bookkeeping that explains why a photon experiences zero proper time on its way from a distant star is, in a very direct sense, the reason your navigation app knows which street you're standing on. Distance and time being frame-dependent isn't an exotic curiosity confined to cosmology. It's stitched into the infrastructure of the modern world, quietly running underneath every turn-by-turn direction you've ever followed. So here's the resolved answer to the question we opened with, the one the algorithm-baited version of this story never quite gets around to answering honestly. Distance doesn't exist for light, in the very specific sense that a photon's proper time and the spacetime interval along its path are both mathematically zero, a direct and well-tested consequence of special relativity, going back to Einstein's 1905 paper and Minkowski's 1908 reformulation. That part is real, rigorous, and about as settled as physics gets. But that zero belongs to light's reference frame, not to yours. And swapping one frame's zero into another frame's measurement is exactly the kind of error relativity was built to prevent. For you, moving through the universe at ordinary speeds, distance is not an illusion. It's a frame-dependent but entirely real, measurable, load-bearing feature of the cosmos, confirmed by parallax, standard candles, particle accelerators, GPS satellites, and more than a century of consistent experimental results. Quantum entanglement doesn't change that either, no matter how many thumbnails claim otherwise. The no communication theorem makes sure of it. The honest version of this story isn't that space is fake, it's that distance turned out to be a much more interesting, much more conditional quantity than anyone before Einstein had any reason to suspect, dependent on your motion, woven together with time itself, and yet still, for every one of us living our ordinary lives at ordinary speeds, exactly as real and exactly as far as it looks. That's the case file, closed with an answer that survives scrutiny instead of collapsing under it. If this kind of evidence-based reframing is what you come here for, there's a full backlog of these investigations waiting for you, including the earlier file on what a photon actually experiences during that zero-time journey, which pairs directly with everything we just walked through. Subscribe if you want the next case delivered the moment it's filed, and we'll see you in the next investigation.